Okay. Maybe Aisha, you want to announce?
Vladimir is going to make the announcement.
Yes, actually. Vladimir.
Okay. Hello, dear professors, colleagues, and friends. First of all, I wish to congrats International Women Days, dear ladies. And I would like to thank you for being here. We have been thinking about organizing this seminar series for some time, and we are happy we finally are able to make it happen. The aim of the seminars is to make connections among mathematicians working on different type of inverse problems and their applications. Now, I would like to introduce Nebojsa Djuric, professor, to present his talk, which is joint work with Sergey Buterin. The title of their talk is Inverse Spectral Problems for Dirac Operators with Constant Delay, Uniqueness Characterization, and Uniform Stability. Thank you. Please give us your talk.
Okay, thank you very much. I will share screen right now, so you have to see my presentation. Good afternoon and happy Women's Day to all ladies. My name is Nebojsa Djuric, and today I will present a new paper together with my colleague Sergey Buterin. The topic of today's presentation is inverse problems for Dirac operators with constant delay, uniqueness, characterization, and uniform stability. Okay, I'm sorry, next slide. When we talk about the inverse problems for Dirac operators, it is necessary to mention the following papers: Gasimov-Levitan and Gasimov-Jabiev solution of the inverse problem by two spectra for the Dirac equation on a finite interval. Both papers are from 1966, and also a book from Levitan-Sargassian. Also, important papers related to other classes of Dirac operators by Bondarenko and Buterin. And in addition, we have many papers dealing with the inverse problems for Sturm-Liouville operators with delay. And we know this is one famous area in the inverse spectral theory. Okay, I will skip these slides. You are probably familiar with all these papers. And in the end, we have some papers dealing with uniform stability of inverse problems for differential operators. Very important paper is marked with Buterin 5 on uniform stability of recovering sign type functions with asymptotically separated zeros. And we will use a lot of theorems from this paper. Okay, introduction. As we have seen in the references in the last decade, there appeared a significant interest in the inverse problems for Sturm-Liouville type operators with delay. And it is known that the compressed square integrable potential vanishing on the interval from 0 to A is uniquely determined by specifying the spectra of two boundary value problems for equation 1 with a common boundary condition at 0 as soon as delay is greater than 2 pi fifth. For many years, there are the open problem for case when delay is less than 2 pi fifth. And the recent series of paper establishes that it is never possible in this case. Maybe you have heard from the media some of these papers. Okay, the present paper opens a new chapter of the inverse spectral theory for operators with constant delay by introducing and studying the Dirac type system of the form equation 2. And we have here the square integrable complex valued functions. When we don't have delay, we have a classical case of Dirac type system. And also, it is important to consider the boundary condition for any fixed pair of Ni and J from 1 to 2. We denote by, we will say B, or this is calligraphic B, but we will say B Ni J of Q, the boundary value problems for equation 2 under the boundary conditions. So we have here 4 boundary conditions, and important for us will be a case when Ni is equal to 1, but also we will explain later why we considered 4 boundary conditions. In the classical case, inverse problems for equation 2 were studied in the Levitan and Gasimov and other works. And there are 2 canonical forms could be distinguished. Canonical form 3 and canonical form 4. And here, with delay, we have something that is very strange. When we, just a moment. So when we have here the diagonal matrix, so the Q12 is 0 and the Q21 is 0, then actually in this case with delay, we cannot solve inverse problem uniquely, and we will describe it later. Moreover, the forms 3 and 4 are not canonical anymore when delay exists because of the non-locality. Moreover, we will see below remark 2 in the next section, reveal that the spectrum of any problem B Ni J may carry essential information only of the functions of these 4. So, for this reason, we assume everywhere that condition 3 is fulfilled. So this canonical form we will use. Actually, this is not canonical form for operator with delay, but we will use this accentuation in whole paper. Okay. Next slide. For simplicity, we restrict ourselves to the case when delay is greater than p half, and in that case, depends of the characteristic functions of the problem on Q of x is linear, and also the nonlinear case requires separate investigation. And so I'm glad to present actually this paper on this seminar, because I hope it will be a lot of paper from this area, and we have a lot of material for researching. Okay, next slide. Theorem 1 actually is well-known theorem for other types of operators, similar operators, and also it holds for these operators. Actually, the problem B1J has infinitely many eigenvalues of the 4. And actually, we have similar theorem for Sturm, for operators Sturm-Liouville type. Consider first the following inverse problem. Inverse problem 1, given 2 spectra, find the functions p of x and q of x. And we have another inverse problem inverse problem 2, given two subspectra, find the functions. So the inverse problem 1 is much more simpler than inverse problem 2. However, we will solve both problems, and also we will use some notation that are more complicated because of inverse problem 2. However, I recommend to some beginners in this area first to try this, to solve this inverse problem 1, and then they will understand some properties of these operators. Okay, as we will be seeing below, inverse problem 1 is overdetermined, as well as the analogous problem for the Sturm-Liouville operators with delay. So we have also similar properties for the Sturm-Liouville operators with delay, and actually we use same forms for this paper. Also, I will say some words about uniform stability. We know that the uniform stability of inverse problems for the classical Sturm-Liouville and Dirac operators in the self-adjoint case was studied in Savchuk. However, we use different approach suggested by Buterin for other non-local operators. An important part of that approach was the proof of the uniform stability of recovering the characteristic functions of operator under consideration from its zeros. Okay. And here we will have one important remark. Actually, we have some important result in this paper marked with Buterin 5. Next important remark related with uniform stability. In the above mentioned classical cases, the uniform stability of the inverse problem was studied only in the self-adjoint case, and it takes place only when there is a non-reducible positive gap between neighboring eigenvalues. The restriction was explained by papers by Buterin, and it is connected with the fact that spectra of these problems B11, B12 cannot intersect if delay does not exist. However, the pictures become completely different when delay exists, and moreover, the corresponding operators are non-self-adjoint, and they may have multiple eigenvalues, which also does not affect the uniform stability. So we will have some interesting properties for Dirac operators with delay. Fundamental solution and characteristic functions. We denote with big Y x lambda the fundamental matrix solution of equation 2. And here we have one important notation. We actually solve the general case. It is natural to have two boundary conditions. Since we have 4 boundary conditions, we use general case to solve it by matrix. When we have, for example, 2 boundary condition, when n is 1, then we will use only vector, not matrix. This is important notation. Eigenvalues of problem coincide with zeros of entire functions, which called characteristic function, also well known from inverse problem for Sturm-Liouville operators with delay. We use a Lagrange method of variation of parameters to establish the matrix functions of solution, and also we solve equation 8 by method of successive approximation to obtain the formula 9, and also when delay is greater than p half, then we obtain the equation 10. Also, it is well-known methods from other papers of Sturm-Liouville type with delay. And finally, when we put that x is equal to pi, we obtain the characteristic functions. Since we have 4 boundary conditions, we also have 4 characteristic functions, and we have here all 4 characteristic functions. These first two characteristic functions are related when n is equal to 1, and the second second two characteristic functions are related when n is equal to. And from here, we actually, okay, I just have to say that what mean the big V1 and big V2, we have some additional notation. And it is important to see that these characteristic functions depend of these form of functions. And we actually justify our assumption free. Okay. Remark 2, a representation of these characteristic functions show that the spectrum of any problem may carry essential information only on the functions of these forms, and only on the mean values of these functions, which justify our assumption free. Moreover, it can be easily seen for the informational point of view. It is sufficient to specify the spectra of any pair of problems with one common boundary conditions, and we will use case when n is equal to 1. So we will introduce some new notation. Actually, we will consider these two characteristic functions, and this function will be delta 1 function, and second will be delta 2 functions. Okay, and finally, we can obtain these 4. So these actually form of characteristic functions is much more complicated than some other forms, but it is very important for inverse problem 2. So we have inverse problem 2 when the 2 subspectra are known, and we have to obtain functions p of x and q of x. However, if we have inverse problem 1, then we can just write these characteristic functions much more easier, and then we can actually obtain these functions on such easier ways. Okay, and when the whole spectrum is known, then we construct these characteristic functions. We will prove that theorem below, and using a Fourier basis, we can obtain functions omega 1 and omega 2, and then from omega 1 and omega 2, actually from equation 19 and equation 20, we can obtain functions p of x and q of x. Actually, this is idea for solution of inverse problem 1. Inverse problem 2 is actually more complicated, but there are some advantage. The advantage of subspectra is that we don't have to construct characteristic functions, but use it zeros. when we put eigenvalues in equations 17 and 18, we will obtain the zeros on this left side. And then from the right side, we actually can obtain some Rees coefficient. And then we can use some Rees basis to obtain functions omega-1 and omega-2. And then from omega-1 and omega-2, we can obtain functions p of x and q of x. So this is idea to solve inverse problem 2. Okay, next slide. By standard approach of involving Rocher theorem, one can prove the following assertion, which can also be obtained as direct corollary from general theorem 4 from this famous paper. And I will skip this lemma 1. Actually, actually this lemma 1 is important to prove theorem 1. Okay, now we have section related entire functions, and we just use another forms for characteristic functions as we have seen in equation 17 and 18. We have a limit of integrals a minus pi and pi minus a. However, we use in equations 21 and 22 the limit minus pi and pi. It is just another notation, but these functions actually will be zero on these intervals from pi minus a to pi. Okay, and now we will use some important theorems from other papers. Okay, functions delta 1, delta 2 are uniquely determined by specifying their zeros. Moreover, the following representation hold, and also we have some similar results for other types of differential operators. Also, we use, actually in proof, we use theorem 5 from paper Buterin 5, marked as Buterin 5. We can skip this. Also, lemma 3, for any complex sequences, lambda n 1 and lambda n 2 of the form 5, the functions delta 1, delta 2 constructed by formula 23 have the forms 21 and 22. And also, it is also well known that these functions are actually equal to these two functions. Okay, next slide. Now we have lemma 4. It is also lemma from this paper Buterin 5 for j from 1, 2 and any fixed positive number r. There exists number c such that the estimate holds when as soon as these inequalities is fulfilled. Okay, and now I want something to say about multiplicity of eigenvalues. So these type of characteristic functions can have a multiplicity, and actually it is important in the segment of Rees basis. So actually we can construct Rees basis on such a way, this way, and where this actually Ni represent the multiplicity of eigenvalues. Also, this is idea from some idea from solution of inverse problems for inverse problem for Sturm-Liouville operator with delay. Now we will speak about solution inverse problem, and also we use this idea to construct Riesz basis, and also maybe we can also use assumption that these eigenvalues can be simple, but it is not much harder to do when actually we have multiplicity. Okay, and now previous idea that I have talked, actually when we construct these functions omega 1 and omega 2, then we can uniquely determine the function p of x and q of x. And here is algorithm for that. Okay, and we actually just have solution of that problem. And also we have some estimates. Okay, and we have necessary and sufficient condition for the uniqueness of solution of inverse problem 2. The solution of inverse problem 2 is unique if and only if each of these systems is complete, is in this space. So we have here two systems, one when j is equal to 1 and another when j is equal to 2. And also I have spoken about it in previous slides. This proof, I will skip this proof. Actually, I speak about this idea when we consider the characteristic functions 17 and 80. And this is actually a method how to obtain the Riesz coefficient. Okay, and okay, this is also a proof of this theorem. I will skip the proof. And also the next theorem provides sufficient conditions for the solvability of inverse problem 2, in sense that for any complex sequence to be a subspectrum of the problems, it is sufficient to have these asymptotics. This is some properties of the subspectrum. Okay, I will also skip the proof. And finally, we have algorithm 1 for solving inverse problem 2. Let two subspectra be given. Then we first construct these functions by formula 25 and this coefficient by formula 32. Then we find functions omega 1 and omega 2 by this formula, where we use Riesz bases that are B orthogonal to bases En1 and En2, and this is important properties. So we have to use B orthogonal bases. And finally, when we obtain omega 1 and omega 2, then we, from omega 1 and omega 2, we construct the functions p of x and q of x by formula 28 and 29. Okay, and we have some more properties for subspectrum. This is related when actually delay is of this form, but also we can skip this theorem. Okay. And finally, we have theorem 5. For any sequences of complex number lambda n 1, lambda n 2 to be spectra of some boundary value problems, it is necessary and sufficient to satisfy the following two conditions. So the sequences has the form 5. This is actually some asymptotical behavior of eigenvalues, and also these functions where delta 1 is given with this equation. Actually, we construct functions delta 1 and delta 2 from these spectra with this formula, and then these functions, actually the exponential types of these functions do not exceed the value of pi minus a, and also this is one theorem that is well known from the other paper. Okay, and we will skip the proof of theorem. And finally, we have theorem 6. Actually, it is a corollary from before lemma. Actually, for any fixed positive number r, there exists some constant such that following estimate holds as soon as these inequalities are fulfilled. So this actually we have the actually properties of uniform stability of inverse problem for Dirac operators with delay, and we have actually here the proof. Actually, we applying the lemma 4 that we have talked in previous slides. Okay, and finally, we have the solution of inverse problem 1 at the end. No, the algorithm 1 can be also used to solve inverse problem 1, but we have some simpler solution of this inverse problem 1, and this is algorithm 2 for solution of the inverse problem 1. So we have here we have to construct these functions delta 1 and delta 2 by formula 23, and then from the 17 and 18 we find functions omega 1 and omega 2. We actually here have simpler for these functions, and in the end we construct the functions p of x and q of x by formula 28 and 29. So this is a simpler way, but here we actually lose sometimes to construct these functions. So also inverse problem 2 is very important and has a significant application. Thank you for attention. So I suppose Sergey wants something to say.
Well, thank you for your efforts. That I think the talk is very good. So I think you said everything. Maybe there will be some questions, and then we can decide what to maybe explain some places, or maybe to repeat some formulations and so on.
So maybe first I want to say Guten Tag alles zusammen. Though I have no questions because it was clear. It was good presentation. And I want to say, how are you? For example, Vladimir, what do you want to say?
Thank you for your questions. Very well. How are you?
What about Piccola?
He is very good. I'm now not in my hometown, and because that he not attends this presentation. In the next Professor Piccola also will be here.
Okay. Best regards for him.
Thank you. So is there any more questions about this talk?
May I ask some questions? The first question is, you said that if we have two complete spectra, this problem is overdetermined.
Yes.
Is it always overdetermined, or it depends on A? For example, if A equals pi over 2, is it overdetermined or not?
Yes, it is overdetermined.
Even for A equals pi over 2 is overdetermined, right,
Yes.
Sergey?
Yes, sure, of course. No, so it's clear. It follows. It's not even follows. It's clear from I don't remember the number. Which theorem it was?
Okay. Wait.
So it's a theorem about necessary. The first theorem. The second theorem. About
The second theorem. I think it is below. Okay.
It's
So
clear because the interval is less.
Yes, interval is less.
unique if and only if the system is the system is complete in this space. So this means that if A equals pi over 2, then it means that minus pi over 2 and pi over 2. So and nk equals 2k, so it will be complete. So it means that it's always enough to specify half of the spectra, halves.
And I understand that you did not study the case when A is less than pi over 2, but maybe could you guess, will the situation be the same as for the Sturm-Liouville operator? That there is the case when A from 2 pi over 5 to A over 2, there is also the unique solution, but when A is lower than 2 pi over 5, the solution is not unique. Will it be the same or not?
Yes, I think that you are right. I think that we have the unique solution when delay is greater than the value 2 pi fifth, and that we don't have a unique solution, but also we will have to prove it. We did not prove it already.
Then I see that you used these results of the recent paper by Sergey Buterin on entire functions, on the uniform stability of recovering the entire function by its zeros, right? But I know that from Sergey that there are also the results of Khrinev concerning the same issue. Are the results of Khrinev sufficient for your for this problem, or they are insufficient and you use Sergey's results?
So which result do you mean about the characteristic function?
About the uniform stability, the results of Khrinev about the uniform stability of recurrent characteristic function by its zeros.
No, I can ask. So you see, Nebojsa, could you please open some slide about the form of the characteristic function? No, just some formula of the characteristic function with integral. Nebojsa.
Oh, okay. I did not understand. Can you?
I mean some formula of the characteristic function.
Okay.
Or maybe even remark one. Oh, it's better to have remark one.
Okay, I was in
This formula.
Okay, we have this formula. Okay, this formula.
This formula, yes, and the remark one.
Okay, I will back on remark one here.
So there is some text about that particular partially answer your question, but your question deals with namely a characteristic function. So in Greenev's paper, uniform stability of the characteristic function was studied only for the case that corresponds to the self-adjoint operator. So this, in particular, this means that he uses analytic properties of some abstract mappings, and for that reason, it's crucial to assume that zeros of this function are separated completely. So this means that not only asymptotically, but separated, and the corresponding operator is self-adjoint. So they are real and separated. But so this result may be useful, but it is restricted to obtain the results under the corresponding restriction. So one should assume unnatural restriction that eigenvalues are real, and unnatural restriction that they are separated. But here it's possible and very common the situation that they are not only not separated, they are even multiple and so on, and not in complex, and so this means that in order to obtain this results for this situation, it's necessary to use such theorems. So another point. So in this remark, it's specified that so the difference between results on uniform stability for the classical situation, for the classical inverse problem, and uniform stability for the non-local situation. The problem is that the difference is that in classical situation, the spectra don't intersect. So spectra of different problems with one common boundary condition. So this means that that requirement of separation of eigenvalues is essential. So it cannot be removed. Never can be removed. But for the case of non-local situation, the spectra can intersect. Any finite number of eigenvalues of the two problems can be common. And even in this situation, the uniform stability holds.
I see. Thank you for your answer. So in your problem, it happens that these two spectra they are cannot be said that they are independent on each other.
They are completely independent. It's the same. No.
If we take the minimal number of data, then these two spectra are independent.
Yes. So if we for example, consider there are a theorem about the so-called M subspectrum. So the M subspectrum, for example, so M spot of the spectrum. M subspectrum, one M. So
yes, I remember the theorem. So you can take arbitrary numbers.
So yes, and this M subspectra is
arbitrary.
Minimal. It's minimal input data. any restriction to this sequences to be the spectra is asymptotics. So they can be common in any number of elements.
Okay, thank you.
Thank you for the question. So it's almost the same situation like in our paper about interdifferential Dirac operator. But in our case, there are asymptotics and there are some small condition.
Yes, in our paper, there was some relation between these two spectra, but in this situation, there is no relation.
But this relation is puts very small restriction. So it is the same for operators in our paper. For the problem in our paper, also any finite number of eigenvalues can be common.
In fact, you can say that this that in the classical Borg problem there is also a small restriction because it's a restriction only on the finite number of eigenvalues. For large eigenvalues are interlaced because of the asymptotics, but only on the finite number you need this interlacing condition.
No,
it's also a small restriction.
You mean interlacing condition, but if you speak about the uniform stability, that this restriction that they should be separated, it concerns not only finite number, because this finite number, of course, it's only finite number, but this finite number can be in infinity. If you speak about uniform stability. But if you
speak about Savchuk and Shkazikov results, in fact, they have this restriction only on the finite number of the first eigenvalues, because in the space that they consider for large n, they don't need this restriction.
But why?
It's automatically false.
No.
Yes, for the spaces W2 alpha, they have.
Yes, it automatically holds because of another condition. Another condition that kappa,
the norm of this remainders is small.
No, that's not small. It's not small. It's just bounded by any finite, but any number, but fixed. So this means that yes, it automatically means. But you see, this no, it's not right, because so it's not right because restriction. So if the norm of the remainder is bounded, it means nothing, because in the row plane they can be multiple also in infinity.
Let us discuss this question later because it doesn't concern this talk. Thank you.
Okay.
Is any additional question or discussion? In that case, thank you very much for your talk, and thank you very much for attendance, all colleagues. We will see very soon again.
In 2 weeks.
Thank you, Nebojsa.
Okay, thank you
very
much. Bye-bye.
Bye.
Bye-bye.
Bye.